Hello, everyone. Welcome to the webinar, to the Deeplite webinar on AI sustainability. My name is Anastasia. I do marketing at Deeplite. With me today, I have our webinar moderator, Dean Bubley, and panel presenters, Mohak Shah, Rob Aitken, Nick Romano, and Rob May. Before we start, just a couple of housekeeping items. This session will be recorded and also we'll send it to you in a follow-up email. We do want this to be as interactive as possible, so please ask questions or make your comments in the dedicated box on the right. If we do not get to answer all of your questions during the session, we will follow up with a blog post later on. That's about it. Without further ado, I pass the word to Dean. Over to you, Dean.
Thank you very much, Anastasia. Hi and welcome. I'm going to be the panel moderator today. I'm Dean Bubley, also sometimes known as Disruptive Dean is my Twitter handle. Some will know me as that. And I'm a technology industry analyst and futurist, and I cover a whole range of areas from wireless networks and 5G to edge computing to IoT, and also some stuff around video and voice communications as well. And some of what we're talking about today is right in the intersection of a whole set of technology trends. And we've got an interesting set of panelists to discuss what's happening with, in particular, edge AI. And I should probably get a little bit of background here is this, I know some people on the call who will have very, very different views of edge computing, with edge AI as a subset of that. And I've been following this for some time, and one of the things I've noticed is that often people don't even speak the same language. There's about 10 orders of magnitude of difference between different people's perspective of what the edge is. And for some people, the edge is a regional data center in a mid-tier city, perhaps. And in others, you've got all the way down through a server and a cell site that can provide compute, down to an IoT gateway, down to a device, and down to an individual, perhaps camera or processor or MCU. And so in a way, you've got edge compute spanning everything from a milliwatt to a megawatt of compute power. And I think that means that there's a whole diverse set of people who don't always realize that they're part of that continuum. And I think that that's got a whole bunch of implications in terms of assumptions that people put into their technology business model. But also it plays into the central theme of today, which is around power consumption. And how do we optimize the amount of energy that goes into certain classes and tasks and workloads for AI and neural networks. And it also has other implications around latency, around privacy and compliance and regulatory. So this panel, we can't answer everything and give the entire future of artificial intelligence, neural networks, and how we optimize for energy consumption across the board. But hopefully we'll be able to sort of start some conversations and also introduce some people to different parts of the value chain that they may not even realize that they're on that continuum. And so with that, I'd like to now turn over to our panelists and maybe ask them to sort of introduce themselves and give a quick introduction. And I'd like first off to go to Nick Romano, who's CEO of Deeplite and obviously one of the sponsors of this session. Nick, over to you.
Thanks, Dean, and thanks everyone for joining the webinar today. Again, Nick Romano, I'm the co-founder and CEO of Deeplite. And I think when we talk about edge, Deeplite is more focused on sort of the milliwatt side of that spectrum that Dean just described. So, our thesis here is that the edge is going to be bigger than the cloud. When we talk about billions of edge devices that are out in the field, containing even more billions of microprocessors, microcontrollers, sensors, etc. If we can unlock the potential of getting AI into these types of devices so that they can process data at the point of data capture within these devices themselves, we truly believe that's when AI will truly become untethered, decentralized, and really ubiquitous in the things that we use every day. And that's what Deeplite's all about. Our core platform is really designed to take deep neural networks that are maybe too big, maybe too slow, maybe too power consumptive, and transform them into a form factor that they can be deployed into these low cost, low power CPU type processors to run inference at the edge.
Right. Well, one thing I think we should probably mention, thank you very much for that, Nick, is that the difference between inference and learning, I think is something that people don't, I imagine a lot of people on this call will know that, but it might be worth just like a 20-second overview for people who are relatively unfamiliar with that.
Sure. Yeah, I'd be happy to do that. So, when we talk about, when I mentioned accuracy or training a model, it's really about training a model is kind of like training a child, quite frankly. They go to school, they learn, and that's how they perform based off of those learnings. So deep neural networks are no different. You have to train them, and that's how they become good at what they do. And the quality of that goodness is really what we call accuracy. So that whole training process, where you use just an awful lot of data that's required to train a neural network, and the more complex the use case, the more data that's required. There's a tremendous amount of compute power that's required to do that. I think we're going to talk quite a bit about that over the course of this hour. Inference, on the other hand, what we mean by that is that's once the AI is trained to do its job. Inference is the actual process of it doing its job. So it's processing data, capturing data. If it's a camera, it's looking at a frame, and then it's making a decision. And it's making a decision based off of the training that it received. And if it's good at what it does, it will make good decisions on behalf of whatever the purpose is. And if it's a really important decision like stopping a vehicle, then you want the training to be very, very good so that it actually does stop the vehicle.
Great, I really appreciate that. That's a good intro for people who might be a little bit unfamiliar with that. Next up, I'd like to introduce Rob Aitken, who's a fellow at ARM. Rob, if you'd like to sort of give a few words.
Sure, thanks, Dean. As Dean mentioned, I'm a fellow at ARM Research, and ARM is effectively everywhere in the range that Dean described, from the milliwatt to the megawatt, just spanning data center down to edge devices. And so we're very concerned about the performance per watt of our designs, and that really feeds in a lot into some of the topics that we're discussing. And basically, there's my grandson is here. There's a starting point where we have the idea of we're going to have an indirect influence, essentially, as an IP company. So we're not building computers ourselves, we're licensing the intellectual property that other people are using. And historically, what's been happening is, as Moore's law has gone along, there's been more performance available, and essentially people have used the additional performance to do more compute. But when you think about a sustainable future, you have to think about, what if we stopped doing that, actually? What if we tried to, instead of doing more compute in an ever-expanding performance envelope, what if we constrained the performance envelope and then shrunk the power envelope as a result? And it's a different way of thinking about edge compute, especially down at the milliwatt level, but it's one that I think has a place in the future. As Nick was describing, that if the more compute that we can push out to these edge devices, the more we can save globally, and the more we can target their applications directly to what they're doing. So I think there's both a potential benefit from a performance and application standpoint, as well as from an environment and sustainability standpoint.
That's really encapsulated. Thank you for that, Robin. Do you have any sense for sort of roughly how big of a deal this is in the big scheme of what we currently do for, whether it's AI or cloud workloads generally? Is this actually a sort of a significant amount of that? Can we quantify it anyway, or is that difficult to do at this stage?
It's very difficult to quantify. You can sort of add up how many edge devices there are and what their overall compute power is, and you can take a stab at how often they're running. Something like a camera is running most of the time, something like your phone is mostly idle, and you can figure out how much compute power that is. And it's actually it's quite a big number. It's a substantial fraction of the world's compute capability exists, for example, in mobile phones. But most of it isn't really doing very much. And you're watching your cat video or whatever. But there's a potential for it to do a lot more. And I think that's really one of the topics we can explore in this panel, is how we can harness this compute power and do something interesting with it.
Excellent, great. Thank you, Rob. Yeah. I'd now like to turn over to Mohak Shah from H1. Mohak, if you'd like to go ahead and introduce yourself.
Thanks, Dean. Hi, I'm Mohak Shah. I'm currently leading our global efforts around data science and machine learning at H1 Insights. I come to this discussion essentially from a machine learning and AI practitioner perspective. We've worked in the field over last about close to 2 decades, looking into broader algorithmic issues as well as sort of the use cases now that are driving various industries and various utilizations of AI from both a demand perspective as well as sort of the limitations on this learning algorithms. Coming from sort of background in more offerings that were very directly interfacing with the user, we have been looking into maybe 3 or 4 core demands of AI learning algorithms, both from an inference perspective and learning perspective. So Nick, thanks for kind of delineating those two, makes my life easier. We've been looking at issues like personalization, for example, or hyper-personalization of these devices. This is where we typically traverse the boundaries between the inference as well as the learning elements, where we can look into pre-trained models that can essentially be customized to the user requirements as they are being used. We have also looked at things like autonomy of these models. How self-sufficient are these models? How much interaction do they have to do with sort of the rest of the environment as well as the back end on cloud and sort of intermediary layers in terms of updation as well as reprovisioning. And finally, we have looked into things like latencies of these models in terms of their decision making and how much of that depends on their interaction with the cloud, or how can we improve that if they are kind of self-sufficient on a specific form factor on the device that we are talking about. And finally, of course, there are issues around privacy and security that have been impacting all of the use cases that we look around AI across the spectrum these days. So that would be sort of kind of my background, and I would love to kind of continue our discussion on learning how other kind of dimensions come into play in our broader spectrum.
Well, thank you for that. That's been really, really useful. I mean, when you talk about latency, I mean, what's your typical quantum that you're looking at? Are we talking milliseconds, seconds, microseconds? Again, there's all orders of magnitude there. What's your day-to-day focus of in terms of zeros?
Yeah, so I think from our perspective, latency comes in 2 forms. One is sort of a millisecond or frame per second kind of latencies when we are talking at devices like mobile, for example, especially vision use cases. So those are something that we are looking at, sub-second to millisecond level. But from other perspective, latency comes in a way on how the learning algorithms on the devices, how quickly can they adapt to the new environments. So think of navigation robots or robotic agents. How quickly would you want these algorithms to adjust themselves if the surrounding changes, and how self-sufficient they can be? So for example, if you change the geometry of a room, if you are training like a robotic vacuum or a navigation robot, the robot should adapt to this scenarios, and the learning algorithms should allow you to be able to do that without very high-powered compute, high-powered reprovisioning of the model, because you are working under extremely constrained environments with very, very limited observability of the environment. So that's sort of the other dimension of the latency that we talk about as well.
Great, thank you. And I think I'll come back to that phrase, self-sufficiency. I think is a really interesting one, because I know I talk to a lot of people on the cloud side or on the network side, people deploying 5G and Wi-Fi networks, and I don't think there's as much recognition as there needs to be of, what does self-sufficiency mean for an endpoint? But we'll touch on that in a minute. I'd like to now introduce our final panelist for today, is Rob May, and Rob, if you'd like to go ahead.
Hi, everyone. So I'm Rob May. I'm a partner here at PJC. We're a $100 million seed stage fund investing in early stage AI and robotics companies. And prior to that, I started 2 tech companies. And, I think my role on the panel is I've looked at this space from an investment perspective for a long time. And in the last year, I really sort of came to believe that edge AI is going to become not just a thing, but a very important and very large thing. And it's one of the trends that I see the general market not paying as much attention to, I think, as people should be, because you do have a lot of fundamental tensions around the economics of edge versus the economics of cloud, how difficult it is to, push AI forward with, bigger and better models while simultaneously being able to push the functionality in those types of models to the edge. So excited to talk about some of that today.
Rob, that's great. And I think from an investment perspective, you must see a fairly broad set of things along that continuum. And I suppose this is a question which Rob, I'll ask you, but then open it up. I mean, are you seeing different sorts of programming or application architectures that apply to particular use cases for edge AI, or are we still at the early stages and we can't actually define what the, if you like, the low-hanging fruit is?
It's a great question. And I actually think for the next probably 8 to 10 years, it's going to be pretty fragmented because we've seen a lot of different approaches, right? There are companies that are trying to solve this entirely in software for CPUs. There are companies that are trying to figure out, like Deeplite, that are trying to figure out, like, how can you get these machine learning models to run on a very small, cheap microcontroller that you've put into a device. And there are people working on new types of chips, right? Chips that are, neuromorphic or analog, things that are small and low power and can run these things on the edge. And I think it's unclear, in the history of computing, we've been really focused on one architecture primarily for most of the time. And we're sort of breaking away from that. We're looking at a lot of technologies that have existed conceptually for a long time and people have worked on. They've been in small niche parts of the economy, and those really have a chance to go mainstream. But I think, what workloads they're going to drive, how people are going to prioritize footprint versus performance versus power consumption, and all those things are still being worked out. And so I think we have a couple years before those market dynamics sort of settle in and you can really predict who the winners are going to be and what it's going to look like. But it's a very exciting and innovative time, I think, for this space because of that.
Nick, have you got any thoughts on that from where you're sitting?
Yeah, so I'll kind of echo what Rob was saying. I mean, you've got there's a lot of dimensions to the solutions that are available, spanning software and hardware, including even the frameworks that you can use to create your initial models. I think one of the things that we're seeing is it's really about the maturity of the solution. Has a lot to do with some of the choices that are being made. Folks that are kind of still in the lab, that are focusing, kind of going back to this whole training versus inference, this whole concept of, hey, I still need to get my AI to perform for the task that I'm trying to get it to do successfully. We'll worry about commercial deployment later. So there's these different phases. And that's not quite frankly, that's often when we get kind of brought into the equation. You've got a solution that actually does what its purpose built to do, but now it's how do we make it commercially viable? How do we get it into a form factor that it can be deployed into a device and to be part of the bill of materials that's going to make economic sense for whatever the unit is.
Thanks, Rob. I mean, ARM has, you mentioned, a fairly unique perspective here because you go everywhere from data center down to device and below. Is ARM backing all of the horses at the same time, or do you think that this particular sort of architecture is likely to win? I mean, do you have any sort of vision on that?
It's an excellent question. I think Rob May brought up some of the points that there's. At this point, we're in the vast experimentation phase where we'll look at all kinds of different solutions to the problem. ARM provides CPUs, GPUs, neural processing accelerators, and so forth. all of those have potential applicability in this space. And in many cases, it's due, which one works best for you depends on what your constraints are. If you know your algorithm, if you know what it's going to be forever, a very targeted accelerator is a very good way to do that. It's the most efficient way probably to do it. But if your design is going to change over time, or if you're constrained by a box that you have that has a particular processing configuration, then you may want to approach it differently. And we really have seen that a kind of an all of the above approach really is a good way to start, that you can start from software optimizations to improve the inner loops of your design. You can have instruction sets in your processor that are more targeted. You can use a GPU to do numerical processing and so forth. All of these things work well for given applications. And at the moment, I don't think there's a clear winner. I think we'll see over time that the world will gravitate probably to something like a microcontroller coupled with a machine learning accelerator of some kind. But that hasn't happened completely yet. It's still open what's going to win.
Thanks. So, Mohak, from your point of view, I mean, what's happening on the sort of the AI side of this in terms of the software and architectures, and algorithms that does that play? I mean, if you like, which is the chicken, which is the egg here in terms of the software versus the hardware? And actually, no one's mentioned the network either, which is interesting because I spend a lot of my time looking at network connectivity.
Right. Yeah, in there, from AI perspective, I think we are looking at few different dimensions of it. I think the first is right off the bat. I mean, we need to realize, I think, that the space is still evolving, both on the AI front as well as kind of on the edge and the broader use case front. So I think when we talk about optimization for edge, we may be talking different things, right? So there might be optimization that are coming purely from a memory perspective versus from a compute perspective versus from an energy perspective. And I think we are still evolving in terms of how do we optimize one or the other, or maybe like multiple objectives at any given point of time. So when we talk about like AI algorithms, we are looking at it from two different angles. One would be how can we optimize these algorithms for edge? And again, when we talk edge, we are talking about self-contained devices where I may lose connectivity tomorrow and I might still be kind of self-sufficient in that sense, right? So when we talk about that edge, there are two broad, I think, paradigms in which algorithmic optimization is at least happening. One would be something that is agnostic to hardware. So this is like looking at a learning algorithm, and especially we are in an age where we have highly complex, very large learning algorithms. So what I mean by that, the parameter space are sort of very, very big. And we look at optimizing these algorithms irrespective of what hardware they would go on. So the paradigm there is we just do as much optimization as we can without really bringing sort of the hardware into the equation, assuming that these can be more general purpose algorithms that can really address a whole different range of hardwares. The second is basically looking into a hardware specific optimization, which is where all this, the earlier kind of constraints that I mentioned start playing a big role. So we look into microcontrollers, and we know that there is only so much memory I can really afford to be able to kind of devote to the model. I also have to look into model architecture itself, because there are a whole lot of model architectures that are relatively more amenable to parallelizing the process versus relying on a whole lot of sequential instruction sets to be used for inference purposes.
What's the sort of evolution cadence of that? I mean, is this stuff which is changing on a year by year or month by month or decade by decade? Yeah, because that's going to be one of the variables here. Is what changes fastest?
Right. So on the algorithmic side, I think the evolution has been very, very rapid. So we are seeing new developments sort of every few months, I would say, in terms of techniques that are looking at, say, model compression, or even the techniques that are looking into different architectural designs for broader kind of deep learning based algorithms. Now, that being said, the fundamental principle that I would like to look at it would be from sort of a use case perspective, because That allows us to decouple the algorithmic space from the actual problem that we are trying to solve. So in some cases, for example, we have looked at hybrid learning algorithms. Take sort of like the best pieces that comes out of deep learning around feature construction and layer it out with like a lightweight algorithm on top that allows you to kind of do very quick inference or very quick model adaptation at the edge. So I think from that perspective, from a AI side, we are partly kind of in this very rapid neural network evolution phase, but we shouldn't be disregarding a whole lot of other learning paradigms, especially with the edge framework, that they'll start to kind of make a big difference as well, in conjunction with what we have in terms of neural nets and other models, basically.
Okay. Actually, it's a good question just come in, and there's a couple of others that I'll get to as well, but I've just noticed one that's relevant. What percentage of global carbon footprint is due to training versus running models? I mean, I don't think it doesn't have to be related to gigatons of carbon, but even just in terms of sort of total compute around AI models. I mean, anyone, Mohak or anyone else, is it 80-20 or 50-50 between training versus running, and where do we see that going?
I'd say it's more like 10-90, 10% in training and 90% in running. And it's also interesting, just the question involves carbon footprint. The carbon footprint is actually fairly hard to calculate in many cases. The energy footprint is easier. But you can see even in data centers from the same company, they will have different carbon footprints depending on where they're located and what their primary energy source is. Whether it's, say, hydroelectric versus natural gas, the carbon footprint will be very different.
Yeah.
So there's mostly it's training. I would say training is a big energy inefficient beast, but at the same time, if it's primarily restricted to you run the training once or a few times, and then you run the inference constantly as a result of that. So it leverages well that investment if you do it.
So in other words, what we're talking about today is about optimizing the 90. Yeah, and it's like if you can basically take the 90 from being heavyweight and do it a more lightweight version, whether that's either on the edge or the cloud, that's what we're talking about here.
Right, and we also have to factor in that these systems are often, especially at the edge, doing something real. So the something real has a carbon footprint too. So for example, your smart thermostat consumes more energy than a dumb thermostat, but it's lost in the noise of how much you're saving on your furnace.
This is true. Actually, Rob, a question for you. How much attention are investors paying at the moment on particularly around AI and edge, to energy consumption? Is that compared with latency and performance? Where does that factor into discussions?
Yeah, it's a great question. We look a lot at, because obviously at the seed stage, we're also very focused on what can turn into, sort of big ideas, and we know, energy consumption and the impacts of that matter quite a bit. So we're always trying to triangulate in. Somebody asked a question here about like natural language processing and vision and stuff like that. Most things I think we see in terms of maturity of the AI stack, we see machine vision applications. I think natural language processing is still behind, but if you follow that space with GPT-3 coming out last year, and then the next version of that will probably come out in the next 12 months, which is a huge model that apparently took months and $10 million I've heard to sort of train. I think there's I think we're really looking at the different ways that you can lower those requirements, right? Obviously, it's why companies like Deeplite are important. We've also seen companies that do things like we'll try to pare your data down before you before you run it and turn it into a model and figure out like, hey, you can train a roughly equivalent model with less data. Where we haven't seen a lot of traction, I'll tell you, is in theory there should be more small data approaches to AI at some point down the road. There are other technologies like genetic algorithms, symbolic logic processing, and some things that could be more efficient for certain applications. We haven't seen much traction there. I think everybody knows, if you have children, like you don't have to show your 4-year-old like 7,000 coffee cups before they're like, got it, it's a coffee cup. Like you show them 2 or 3 and they're like, I know what a coffee cup is, and there's transfer learning, one-shot learning and things that we're working on for that. But I think we're still a long way from that. So those are some areas that we haven't seen much traction yet from a technical perspective, but could eventually solve some of these problems as well. But yeah, and then there's a lot of people that are thinking about how do you make all these things, more efficient? How do you use unused compute on certain devices? So it's a huge thing, but I think it's driven by overall more of the performance and efficiency trade-off and the maturity of certain technologies and where they are, more so than sort of maybe direct environmental perceptions at this stage. So although all that said, I will say ESG across the board is becoming a big issue for all levels of investment.
How much do you think is software stack of that? Because ease of programming is certainly something that seems to factor into what solution you might approach.
Yeah, well, that's what's hard, right? Is, as I mentioned at the beginning here, right? Like we've been consumed with this like von Neumann architecture for, 60 years or however long we've been doing compute. And it's the way most things work. And it's the way most programmers think about writing code and everything else. There are many other ways to do compute. But to the other Rob's point, like all of our workflows and software stacks and every piece is kind of set up to work this one way. And so when you're in this experimental thing and you don't necessarily know what's going to work next in terms of what are going to be like the big hit chip architectures of the next 25, 30 years. We don't know, but some of them are going to need new software stacks and some of them are, and some of them are going to need new pieces of software stacks. And like, it's a really exciting, but also complicated time to navigate.
Thank you. Nick, I've got a question for you, which is, what are you seeing as the sort of early use cases for the type of edge AI that you're enabling? Is it sort of single camera machine vision? I'm assuming it's not things where I've got 100 cameras around a city and I'm trying to correlate where are the crowds or something like that. Presumably it's sort of AI which is used at a point for one end device, not linked to others.
Yeah, that's where we're seeing a lot of the activity. I mean, we're having conversations about some of those broader, multi-camera environments, but a lot of the activity and a lot of the when I talked earlier about maturity, I would say a lot of those sort of single camera use applications is what we're seeing. We're seeing quite a bit in manufacturing and utilizing computer vision for defect detection, anomaly detection, that sort of thing. What's sort of fascinating about where we come in, because we don't really develop the models, right? Our job is to work with organizations that are looking to take a model and optimize it for their commercial use. So we're seeing a lot of different types of use cases, which is pretty fascinating just being in our seat here. So everything from toy manufacturers who are looking to have more immersive experiences to, again, manufacturing defect anomaly detection, and then, speed detection in autonomous vehicles, but to your point though, they're all very purpose-built applications that are, that we're focusing on and we're seeing a lot of activity in. But the diversity of those applications is quite fascinating.
Look, I mean, that's interesting. It was a question that I just seen it come up in the chat, which is, where does all this play out? Is it on the industrial IoT edge, or is it more on consumer or vehicles? It sounds like it's fairly diffuse. Is everyone seeing that? Or?
I mean, just from my perspective on the manufacturing side, I mean, manufacturing's typically been on the vanguard of trying to use automation to be more efficient and to drive margin. So we definitely see a lot of activity on the industrial and manufacturing side in terms of trying to use AI and in particular computer vision solutions for practical solutions like anomaly detection. Looking at tools, vibrations, detecting whether a tool needs to be replaced so that you don't end up with defects. Those sorts of things. It's really quite interesting. But that's definitely a big area of growth that we're seeing.
Mohak, are you seeing any patterns like that as well?
Yeah, I think Nick made a good point. Actually, manufacturing has had a lot of use cases. We have looked into those as well. I would just like to extend it a little bit. I think from an edge AI perspective, these capabilities or the potential for those capabilities are much more ubiquitous than we realize. In fact, right, everything from a whole lot of dedicated AI capabilities that even go on sort of like modern day mobile phone, right? I mean, everything from like voice processing, for example, that have like dedicated routines that do DSPs on that. They are kind of looking into a whole lot of AI driven approaches now to be able to do voice enhancements, voice optimization. We clearly are looking a whole lot of vision and NLP application, but then there are applications, for example, on headphones and noise cancellations, right? There are a whole lot of applications that are now being integrated into the vehicles. The entire kind of automation on, or like the automation autonomous driving industry, there is like a whole lot of applications there. I think from that perspective, it's more ubiquitous. The other thing that I am also kind of seeing broadly is from training like this arbitrarily large model like GPT-3s of the world, or a whole lot of equivalents that have come out of like Baidu and a bunch of other companies now. In some sense, we are kind of testing the limits of how much these models can learn if given arbitrarily large amount of data. But then sort of looking at it from other perspective, there is another evolution that is happening where we can see the evolution of better understood spaces like vision and NLP, or like language understanding to some extent, would be able to kind of reuse these capabilities, right? So there is like relatively, hopefully, reduced strains on training as we go forward, as this space becomes more and more understood, and be able to reuse this. So I kind of see one trajectory that might evolve out of this would be an industry that would do models as a service rather than kind of AI as a service, right? So I mean, I can imagine sort of like off-the-shelf models that can be utilized for a whole lot of variety of tasks when it comes to vision or NLP and those domains. So that can be an interesting development in this direction as well.
Okay. So what I'm wondering. Sorry, I'm just looking at the comment that's come in from Rob. From your perspective, where do you? I mean, where is the sort of the low-hanging fruit in terms of it? Coming back to the energy side of it, or something like that, which is it about the location-specific applications of AI, or is it how much of it is about the distributed and correlational multi-location AI, would you say? And also from an ARM perspective, obviously you've got interest on the connectivity and wireless and broadband side. Are there some assumptions there that are perhaps not always valid?
So is that for me, that question?
Yeah, Rob. Sorry, Rob.
Yeah. Sorry, we have
two Robs. Yeah, sorry.
Robs here, so it's sometimes. Yeah, I would say there's two classes that I think are interesting. So one is the very localized. Here's something we're looking at, and there are all these verticals that we've been talking about. So there's an industrial, there's some machine someplace that needs to optimize its production, become more efficient. There's a camera where you've got a limited battery on it, say a wildlife camera. You want to make sure that you're not wasting a whole lot of time looking at leaves. So there's various individual applications, and part of the challenge for ARM, or really any company in this space, is trying to figure out how you can build a solution that spans multiple verticals when the verticals are so different and complicated. That's proven over the last few years to be a significant challenge in deployment of edge IoT. But I think there's also in the distributed world, the AI capabilities enable new functionality that didn't really exist before. So, in California, we're suddenly much more aware of wildfires than we've been. And there are all of these networks around of air quality sensors. There's several companies that run them. For example, Purple Air has one. If you look at these, like I was looking at the map because I've got one of them, and I was looking at the map a week or two ago, and it was like, oh, look at that. There's a fire up by Lake Tahoe. And I could tell that just by looking at the distribution of air sensors in California. And this is that kind of stuff. It's like the 4-year-old with the coffee cup. You know, it's like, okay, that's a coffee cup. That's a forest fire. You can start to see patterns pop up in when you have this access to huge amounts of data that you couldn't see before. So I think our challenge is, how do we do that in an energy efficient way? And how do we take what we're learning and make that part of effectively a sustainable society? And I think there are a bunch of opportunities there, and some of them we will stumble on accidentally, like the forest fire one, and others we will try to do quite deliberately, like the industrial IoT.
Right, and I suppose the other side of this is, I mean, I know there's going to be people who I work with who have come from the point of view of, I don't know, wireless networks, 5G, low latency, a lot of discussion around ultra low latency, and a lot of the use cases people talk around are around, it could be environmental monitoring or digital twins or connected vehicles. It strikes me that some of those absolutely need to have that, connectivity and wireless to aggregate the data from, say, the sensors, so you can spot the forest fire. But I'm not sure that's necessarily going to need the sort of famed millisecond latency and all the rest of it. Those tend to be, like, I would imagine, the medium to high latency tolerant things, perhaps needing lots of data. But it's like that trade-off again, I imagine. Do you need to spend all the power on transmitting all the data in real time every millisecond, or do you filter it down and you do updates once a minute or something?
Yeah, that's true. In autonomous vehicles, particularly, that's an interesting challenge, because if you were starting from the ground up, there was no existing system of vehicles. You'd actually want to build fleets of interconnected vehicles that communicated with each other and local infrastructure constantly. But if you're starting with the existing system where existing drivers do what they want and they ignore the infrastructure, then you have to build a completely different set of vehicles that are effectively able to stand on their own and fend for themselves. So.
Yeah, I mean, I'm very interested in the whole area of path dependency and why history matters and why it's quite difficult to change entrenched behavior. That's maybe a discussion for another session. Okay, I mean, one thing, if I see there's already a couple of questions that are coming in the chat. If people, and we had some also submitted in advance. If people have other questions, feel free, and we'll try and take what we can on the sessions, hopefully to weave into the conversation. Otherwise, we'll try and get back to people. One that I know that I've seen that's come up is around industrial IoT, and sort of, that's perhaps a little bit less about the energy side and more around the different tiers of latency and sort of the microsecond, millisecond, on-premise the second. I mean, do we see that type of sort of coordinated cross-layer application becoming more viable? And does anyone yet own that orchestration of where all the workloads go? Feel free to. If no one's sure, then we can pot that on for further study.
I don't know if anybody owns that orchestration. I would say it's still very much a lot of this stuff is being built, purpose-built for the specific applications by the organizations that are managing these assembly lines or these processes. But there's definitely this notion of what are the right uses of AI for different purposes, right? So if you're doing anomaly detection on rolled steel, you may be using very quick, rapid, obviously very fast decisioning to say, hey, we've detected an anomaly, but maybe that information is going to another location, maybe a server nearby, that is basically saying, is this a material defect that requires attention? Or, so you do the sensitivity analysis on what's been detected. And there's just different sort of stages that you can use. And, there's a lot of different applicability to that sort of layering of solutions. Wake words is a perfect example, right? Like you've got something that very lightweight, wakes up a device so that it can do something with a much bigger purpose, sort of thing.
I like that idea of layering. I'll definitely come back to that. Well, one other slightly tangential question before I go back to the Q&A coming in is, there's clearly some questions here around what people refer to as the circular economy and sustainability of equipment and hardware, and reusing as much of the existing fleet of electronic devices and idle capacity. I mean, that's presumably also been thrown into contrast into the spotlight, by the current chip shortages as well. So, and I guess there's both an economic and environmental desire to use what we've got more. Is that what people are seeing at the moment?
I'll say, if you want like an investment-driven example of this, one of the stories that came out, I think about 1.5 years ago was, when Google acquired DeepMind for $400 or $500 million, and people were like, they're just an IP shop. It's a ridiculous acquisition. But I think I read that they were able to apply DeepMind's AI algorithms to save $1 billion a year in electricity across their data centers. And so when you think about the idea of using fewer chips, using less power, they're just using better AI models with more data. There's a piece of this that's going to be able to help in that scenario, and I think you're going to see other similar stories like this.
Yeah, I think that reflects in the circular economy piece as well too, because part of that is reusing something after it's reached the end of its life. And that goes back at some level to what Nick was saying, that a lot of times at time zero of manufacturing, there's some piece of data that tells you that this specific object has its lifetime limited by something. So this has got a future reliability problem, but if you kind of do the arithmetic and say, oh, well, it's only going to last 1.5 years, so what do I care? That may lead you to different production decisions than if you say, well, actually, I want to reuse this thing later, and it's going to have another 5 years sitting someplace doing something else. So there's, I think, a need to be more careful in how we design for resilience and how we measure it and calculate it, so that these products have that when the product's lifetime is limited by whatever the weakest link is in it, that we do what we can to keep that weakest link from killing a very expensive device very early.
I guess there's a flip side around cybersecurity, which is whether the older equipment is as secure as newer, but that's again another discussion, I guess.
Yeah, or whether and how you make sure that there's no confidential data on it if it gets repurposed to something else. I mean, running it through a mechanical shredder is what gets done now, but there are more environmentally friendly things to do.
Yeah, and I don't know, Rob, if you guys are seeing this at ARM, but one of the things that I've seen as an investor in some of the AI chip companies that are coming out is, chips go down this line of process nodes, they call them, with smaller and smaller and smaller, right? And I think they're coming to 3 nanometers now. And so, these old fabrication facilities, eventually, they can produce bigger chips, 14, 50, 100 nanometers, whatever they are, for a while. But at some point, everything's kind of gets pushed down. And one of the things we're seeing is with these new chip architectures, some of them can go back to these older process nodes and use older equipment, and for certain types of workloads outperform what's running at 7.5, whatever process node the cutting edge stuff is. And so from a circular economy perspective and a chip shortage perspective, we may see the ability to use some older chip fabrication technology in coming years to create some of these new types of architectures, which might be beneficial to the economy and the environment overall.
Yeah, no, absolutely. I agree with that. And there's, if especially with, several people have mentioned accelerators of various forms. If you have a particular acceleration algorithm that you want to hard code into silicon, that's easier and requires a smaller design team to do that at 180 nanometers versus doing it at 7 or 5 or 3. And depending on what you're doing, the resulting object, as you say, may be more efficient, because if you have a perfectly targeted device, it's at 180 nanometer, it's a low leakage process, your battery efficiency may be far greater than it would be if you took a leakier process like 7 nanometer and threw because you couldn't afford, a couple $100 million to develop your own ASIC through something that wasn't as optimized at it. There's a flip side of that in academia, where people publish papers that say, well, I built this thing and it is X efficient, and I compared it with a top of the line Xeon processor coupled with a super high performance GPU, and my thing is much more energy efficient. It's like, well, duh. But yeah, that opportunity is definitely there, and I think that's a good one to look at.
Thanks. So there's a couple of questions from someone in the chat, which are probably aligned a bit more with some of the stuff I do day to day on the cellular networks and 5G and what the mobile industry calls edge computing. I realize it's a little bit out of scope for some people on the panel, but I'm curious to know how that fits into the assumptions that may be happening in other bits of the industry. I'll read it out. An adaptive edge platform, which they're defining as an infrastructure that combines different sorts of sensors and adapts to power usage and latency. What if such a platform could be built by combining wireless microcells that work on cellular energy, presumably in the field? And so essentially, I'm guessing the idea is to have a small cell using wireless connectivity to sensors that can essentially try to map the power used for the radio and the power used for the end device sensors and compute with some sort of backhaul when necessary. Is there a role of a sort of wireless node as a sort of an aggregation point for some of the applications we're talking about here?
Yeah, we think so. We've especially something like a harvester-based device like what they're talking about is a really interesting application, because it really can be, as Mohak was saying earlier, just untethered. You can put this thing out there and it can do something. The carbon footprint of such devices is also interesting, especially if you can make them batteryless, because if it's batteryless, then you save a huge amount of energy producing the battery. The energy that goes into making a battery is far greater than the energy that you get out of it. So even a system that's like 25% efficient that runs on a harvester is more carbon friendly than one that runs on a battery. You have to redesign a lot of bits of your system that you wouldn't think, because of the profile of the energy availability. With a solar cell or pretty much any harvester, you have this limitless supply of energy, but a very limited supply of power. So energy comes along, you do some compute, then you notice that it's tapering off. So you've got to fire off whatever radio transmission you wanted, or store something on a flash somewhere, and do that all before basically the sun goes behind the cloud and you're done. So there's a lot of interesting system design problems, and when you link multiple ones together, you have to make sure that they're not just waking up by themselves, broadcasting out into the lonely wilderness to sleep, and then somebody else wakes up 10 minutes later and says, I wonder why no one's talking to me. So there's a system design problem that you have to solve as well.
That's fascinating. Mohak, you seeing anything around that?
Yeah, I think just to add to what Rob mentioned, it was sort of very interesting take on the energy side of it. From a sensor integration perspective, I think one of the other elements that we have also looked into is this whole notion of collaborative learning across devices. So think of broadly within sort of the context of mobile edge networks. Or mobile edge computing, in fact. And the idea there are like these use cases where we can feed off of the compute from adjacent devices within a closed environment. So think of like a smart home, for example. And if you have sort of learning algorithms that are deployed on, let's say, a refrigerator or appliance or something, you might think of kind of, utilizing a common compute source to be able to kind of retrain, update these models without really having to go back to sort of your high-powered sources within this closed environment. And that can be sort of another paradigm that we can look, allowing us to move beyond this point use cases of sort of edge AI for a specific dedicated sensors, all the way to kind of integrated environments that we can kind of provision as a result of that.
And I guess putting my sort of mobile and 5G hat is if that's an outdoor environment with like a smart city or a roadway or something, then there's potentially some interesting opportunities there for optimizing traffic flow in a city or something like that.
Absolutely. And sorry, Rob, go ahead.
No, go ahead.
No, just one other thing I also wanted to add is the efforts that are kind of happening broadly in AI space, specifically around reducing this communication overhead or network overhead. In paradigms such as, for example, nascent paradigms, but paradigms such as federated learning, where you are not really trying to kind of move a whole amount of like big amounts of data across the network, but essentially just looking into kind of moving around sort of basic parameters of these models that can essentially allow you to kind of improve these models as the time goes. So that's been another area that's trying to kind of achieve some balance there.
Yeah, and you can't do that without the network.
Yeah,
absolutely.
Yeah. So,
yeah. And a programming model.
We've got a couple of thank you. We've got a couple of minutes left. I don't know if anyone's seen any other questions which you want to jump on, but there's one I can see about how do we manage a machine learning software ecosystem against the sudden explosion of hardware. Do we just deal with the complexity or see what falls out, or is there any roadmap there?
Well, I don't think you need to go any further than the collaboration that Deeplite has with ARM, for example, to talk about software and hardware coexisting quite nicely, and the force multiplier effect that I think you can get from software and hardware acceleration, and what that can do for applications for sure.
Yeah, I think that's going to lead to essentially it's like the Cambrian. I like the Cambrian explosion analogy in there. There were a zillion different organisms, and they collapsed down to a much smaller set that we see today. And I think we will see the exact same thing happening in this hardware software universe. There will be a small set of things that pop out the other end and work. If I was Rob May, I'd have to figure out who the winners were so I could bet on them. But
it's tough. There's a lot.
Exactly.
Right now,
we know someone will win. Predicting exactly who is very challenging.
Okay, it's often difficult to predict who will win, but you can sometimes predict who will lose more easily. Has anyone seen come across anything you've seen in this space where you think your assumptions are flawed? Yeah, is there anyone you've talked to, or don't name names, and you've gone, no, you completely missed that? My job to be contrarian.
I will say I passed on a company that I know Nick knows, but I won't name the name. That basically believes like there's no reason for GPUs or any of these other chips. There's a lot of unused CPU capacity that you can use to be more efficient. They've got some pretty big backers, but I literally got into a very heated argument. This was pre-COVID with one of the founders on some of the technical issues at drinks one time. Somebody actually had to come and be like, "You guys need to stop talking about this," because he was pretty like aggressively like anti-GPU, and I was just, I don't know.
I think that ship sailed. I know the one that sticks in my mind is lots of people that I encounter keep talking about some stat about how a self-driving car will generate 4 terabytes of data per hour or day or something like that. And I was like, 99.99% of that is never going to leave the vehicle. They were using it as a justification for. Firstly, for needing 5G networks everywhere, and secondly, edge computing to process this massive amount of video. And I'm like, who wants to look at 23 hours of a concrete wall while the vehicle's parked and have to ship a terabyte of data across? I don't know.
Yeah.
Anyway, I think we're about to run out of time. So I'd like to thank all of you and thank Nick in particular for Deeplite sponsoring this. Anastasia, I don't know if you have any last words or you want to mention people how they can follow up with this or what to expect.
Yes, we'll be following up with the email and the webinar recording. So if you want to watch it on your own time, you'll have the opportunity to share it as well. Otherwise, by answering to that email, you can also let us know what are the topics you'd like us to cover in the upcoming webinars. So thank you, everyone.
Awesome. Great. Thank you very much indeed. It's been a really enjoyable session.
Likewise.
Thanks,
All
everyone.
right.
Thank
Thanks,
you, yeah.
Dean.
Thank you.
Thanks, everyone.
Bye bye.
Bye.
Thank you.